Are you ready? Let's start. So, hello everyone. Thank you for joining today to hear the amazing journey of Gousto. I hope you had a very good first day at re:Invent. So, this journey of Gousto is about how they managed to to build data-driven operations using AWS services and partners. My name is Dimitrios Pilopoulos. I'm a worldwide industrial IoT go-to-market specialist, and I have the big pleasure to welcome here with us Thomas and Fabrice from Gousto team. So in the next few minutes, I will cover some challenges we see from industrial customers while they're trying to become data-driven for their operations, and also I will share the AWS approach to deal with these challenges. And this approach is used also by Gousto, and it's a very fascinating journey, what they have achieved, like reducing food waste or increasing worker productivity, and also pay attention how they manage to do this. You can learn and get some good practices. So as a high-level observation, we see that our customers are telling us that they want to accelerate and scale the way they use the data beyond a single use case. And while they're trying this, we also hear customers, and we read in the reports, that every organization wants to be data-driven, but only 1/4 of them is able to be successful. And only 1/3 of them is able to get value out of their data. And why this may be happening? The industrial data, I guess you all face this, is very fragmented and lacks context. And what problems this creates? So almost every manufacturer have high-value industrial data. But this data, as you may know and you may experience every day, is unused. And most of the time is spent to be able to gather the data. We have found around 80% of the time is to gather the data, which means to locate the data, ingest the data, then prepare the data to get some insights. And when you have the insights, then it's quite late to take any decision or react on the data. So it's unused, the high-value data. The second problem is that it's very time-consuming to build a solution. Usually requires 5 to 10 people just to come together for a single solution. And when you want to do another solution, again, you start from zero, which is not very efficient, right? And then the cost. It's very expensive when you have found your successful solution to scale it. The cost is very linear, so it doesn't help with the business case. At the end of the day, our customers telling us that they just want easy access to their data, doesn't matter from where it's coming from. And let's see now the AWS approach. We're looking for our evolving position is about having data-centric approach throughout the life cycle of the data across IT and OT systems. And you can see here 5 abilities that we're looking to achieve when we're talking with customers. First one is accessibility, how you can access the data at the edge easily, like where the data is produced, and also in the cloud. The second ability is about interoperability, which means how you can integrate your existing data with your future data investments and more augment what you already have instead of replacing or starting from zero. The third one is extensibility, how you can add extra business logic while your business evolves. And the fourth one, versioning, which is how to document and document the changes and the relationship of your data, which will help to have the right data governance. And the last, but very important, scalability. Scalability at the asset level, sites, but also use cases in a cost-efficient way and very secure. So this is what we're looking when we're talking about data-centric approach with our customers. And this is also what Gousto has done throughout their journey with AWS. So what is the AWS approach? We have launched some time ago the Industrial Data Fabric. This is an industrial architecture that helps to connect data from different systems and facilitate the data flow through a common API. And there are mechanisms to manage your data and your governance in a secure and scalable way. And of course, to prepare you for generative AI and using your own data and LLMs to build your own applications on top of your data to achieve your business outcomes. And let's see a little deeper about Industrial Data Fabric, what it is. So this architecture is prepared to address customers who are buyers and also builders. Gousto, I think, is in the builder category. So there are AWS services involved, many IoT, for example, like AWS IoT Sidewise or AWS IoT Core, and many other AWS services, and many partners. There are ISV partners like HighByte, and HighByte is used also by Gousto, and you will hear how they are helping them solve many of their problems and build data-driven operations. And there are also system integrators who are able to put all this architecture and ISV partners and AWS services together for all the manufacturers. And so with Industrial Data Fabric, we're helping the manufacturers to ingest the data, store the data, and contextualize the data. And at the end, act on this data. Doesn't matter what is the use case. Could be energy monitoring, predictive maintenance, or other use case with generative AI. And this is an approach that Gousto has managed to put together using a HighByte and AWS IoT and other services, and they have achieved some amazing outcomes. And they will share with you some great numbers and how they managed to do it. Now, I would like to introduce you to Gousto to hear about their fascinating story. But first, let's watch a video about who and what Gousto does in UK. And then Thomas and Fabrice will come on stage to share their exciting journey. Thank you.
Gousto presents the recipe box with the greatest choice. Featuring speedy 10-minute meals, crowd-pleasing family classics, and global cuisines. Prepare for fresh, quality ingredients and blockbuster flavor. From only $2.99 a meal. Critics are raving. Now cooking in a kitchen near you. Visit gousto.co.uk.
At this late hour. My name is Thomas, this is Fabrice. We're going to tell you a little bit about how we went about it. So a couple of years ago, I came across this question. If you had access to the state of everything, and you could reason on top of it, what problems could you solve? And I personally found that very inspiring, but it didn't reflect really the situation we were in. Because the reality was that we were incurring $30,000 per hour every time we were experiencing downtime, and we didn't know how to solve it. Because the reality we were facing was that we didn't know the state of anything. We couldn't reason on top of data we didn't have, and therefore we couldn't solve any problem. So how would we prevent this downtime and incur this massive financial penalty? So for that, we needed data. And so we went about trying to create a vision. Where do we want to end up a couple of years later? And we reasoned that, first of all, we have data in our assets. We need to somehow get hold of it. Once we connect to it somehow, we didn't know how, we need to take it somewhere else and make it better, make it usable, useful to other functions that are going to use it. And once we get it there, we can then start shifting it into systems that can reason on top of that data and start adding value. And more importantly, turn this into actual decisions that we can apply, hopefully optimal decisions, not just decisions. Turn this information into commands back into the factory so that we can control it, alter its state to our favor, and then start preventing some of these problems we were facing. So Before we kind of go through all of that, a little bit about ourselves, and we're going to then take you, we're going to break down the challenge, make it a little bit more concrete, and then we're going to talk to you about the solution, which we called Factory OS. So it's like a brand name we produced for our product. It's effectively the operating system to our hardware, which is the factory. And then we're going to tell you what we're going to do next. So we've gone from 0 to 1, and now we're just planning our next steps. And after that, hopefully, we'll talk a little bit about how it might be useful to you. So let's talk a little bit about us. So you saw from the video, we are a meal kit company. Basically, we deliver boxes like that, full of fresh ingredients. And we're all about the best choice. We kind of tend to focus to a very broad range of customers. We target a very broad market and multiple household sizes, 1, 2, 3, 4, 5 people in a family. We tend to try, especially for taste, very large variety of recipes, as broad as we can. This is really our main strategy. We tend to cover for most budgets, cheaper, more expensive, and multiple meal occasions, mostly dinner, lunch, soon perhaps breakfast. So a very broad market, and that makes the problem more complex. Our mission is very, very simple. We just want to be the most loved way to eat dinner. That's it. That's what we exist, and emphasis on the love, and it's important to us. And we want to do all of this while enriching your lives and also leaving the planet in a better state than we found it. That's also very, very important to us. How do we live this? Really, from the moment that our customers shop, place their order in the app or the website, to the moment the box arrives, unboxing it, and then preparing it and finally cooking it, all the way up to just enjoying the food, which is what it's all about. And eventually the feedback we receive, which is usually very, very good, and we keep trying, of course. So it's all about choice for us. We do 200 recipes and every week, and they're not slow, sort of slight variations. They're just unique and distinct recipes, so we can cover as much variety as possible. And we try to keep the waste as low as possible, and we keep on improving that. So that's a little bit about us, but what was the challenge we were facing?
Our challenge was to ramp up our production. So around 2 years ago, we opened a brand new factory. And to give you a sense of the size of the problem, we are producing 200,000 boxes a week, which means we have to pick and pack a box every 3 seconds. And every one of these boxes is made of like 50 unique different ingredients. So that's quite a large-scale problem, like 10 million picks a week. Now, when we opened that site, we were able to work it at up to a third of its picking capacity. The problem was the availability was fluctuating quite a bit, between 70 and 85%, but we didn't really understand why that was. We had no clear links between the events we were seeing on the floor and the action that was taken by our people. The faults that we were encountering were not fixed very quickly, and we had no real feedback about the repairs that were done. Our engineering team could only analyze the issue after they've happened and after they've been fixed, not very much in time. And obviously, there was no way to provide any analytics about potential recurring pattern, recurring issues. And so our confidence was a little bit low back then, and we were asking ourselves, can we really scale this site, this factory? So first, we had to understand what was our real net production. So if you take all the hours available in a week, then you remove the hours where your site is not used. You also remove the time where you have unplanned downtime, like the time when people go on break or the planned maintenance. After this, you're left with the time where your equipment is not used very efficiently, and that can be from a number of reasons. Once you've expressed all of these different fractions of that time, you end up with the remaining productive hours, and we were able to measure that every 1 hour of lost production was costing us $30,000 an hour. So that was the size of the prize. Having access to this, we were able to identify our lowest hanging fruits. So for this, we use that OE equation, which is made of these 3 important terms. First, you have the availability of your equipment, then the performance of running it, and the quality of running that process. And you can identify these three terms independently. Having access to that data, we were able to identify that availability was the real bottleneck in our site. And we needed to bring this metric from 70% up all the way to 95% in a short amount of time. That's how we could run our site more efficiently. And after that, the vision was to bring that level of availability even further, up to 98.5% in the long time. And I'm happy to report that today we're running the site consistently at 98%. So we can say that we've done it. This is done. But how have we done that? We've broke the journey with 3 very simple steps. First and foremost, the most urgent was to be able to detect the downtime as fast as possible. Once you're able to detect the fault, what you want is to minimize the mean time to repair. And once we achieved that, we were able to focus our attention to maximizing the time between faults. And that's how we've gone about our journey. And now Thomas will tell you about the solution we've put together. As we said, we've called it Factory OS.
Thanks. So how did we go from 0 to 1? I went and asked the head of engineering, what does good look like? And he said to me, when a fault happens, get me an engineer, exactly where the problem is, tell me exactly the location, what the fault is, and get it done fast. And while you're at it, make sure you capture the data so I can use it later on to make some analysis, learn from it, so I don't keep repeating and reacting all the time. So that made sense, but the reality was a little bit different. Instead, the equipment would go down. Maybe somebody would spot it with their eyes. Basically, anybody with eyes would just spot the problem, some jam or whatnot. And maybe they'll find an engineer, and they will go and say, hey, can you please fix it? Are you the right person? Can you find the right, would we have slack? And eventually, they would find an engineer, and they'll kind of talk amongst themselves, and the right person will end up going there, fix the problem, and if they remembered, they will update the system. So most of the time, we didn't know that the fault even happened. And so you have a situation where technology follows the people. And when you see how that impacts the mean time to repair, it's kind of quite stretched and full of waste in between. So we thought, okay, what can we do? Well, how can we flip this? How can we flip the script here? And say, okay, equipment will go down, but instead of people trying to figure out what happened, why don't we just take the data and invent this thing that will detect faults. We didn't know what that was yet. But we'll ingest the data, and hopefully it'll reason that, yes, this looks like a fault. Not every kind of signal results to a fault. It could be false. And then create an order into our maintenance system and dispatch the engineer, fix the problem. The data is already in the system, so we don't have to ask them to do it. And as a result, now people follow technology. And you can see that when we did this, the mean time to repair collapsed. And we discovered more. We could now start tracking other things that we couldn't before. So when something breaks down, you can actually discover that. You found that something's broken down, and then you just told an engineer. You can start saying, how fast did they go to that problem? How much time did they spend to investigate that? And then how much time did it take to repair it? So the whole cycle is now tracked quite granularly, and we can just optimize each step, and the MTTR is collapsing continuously. So that was a much better place to be, and we still had in the beginning, we're still now at 0, and we have a very fundamental problem, is that our factory has equipment, like most factories do. Most have PLCs, and in our case, we had good PLCs from Siemens, very good data, good models, so we didn't have to try very hard. We had, for those who are more familiar with this stuff, we had PLC servers controlling those PLCs. We had Kepware running OPC UA. So basically, it's a very good setup. But the problem was that the data was locked. We couldn't just act. It was just sitting there, untapped, and we were just not using it. So in our case, we used HiByte. It's an amazing platform that allowed us to connect to the data and bring it out of the automation. But that was just half the story. So the data is now out of the automation, but we kind of need to break it to the cloud. Because once we do that, we have a team that's about 200 strong. They're all cloud engineers that do software, data scientists. All of these people can now actually work on the data and start making good use of it. And so the second piece of the puzzle for us was to route this data out to AWS IoT Core, which is effectively an MQTT broker. And together, these two pieces, this is how we see what is commonly called in the industry these days as the unified namespace. So that for us was ground zero. This is kind of where we created our most fundamental component, our foundation for everything that was to come. I want to touch a little bit on HiByte because for us it was a game changer. Without HiByte, we just could not have done any of this. So it allowed us, before I go to that, actually, we tried to build this ourselves a year before all this started, and we utterly failed. We spent a team of 10 working on this for a whole year, and we failed. It's a hard problem to solve, and we shouldn't have to if we can buy it. So HiByte allowed us to connect to the data natively, and it was just there. So that's a big step forward right there. Literally within 2 days, we were connected. We can model the data. So every time we have a new PLC turning up, we don't now have to we don't have to create it from scratch. We can just instantiate it through templates, and we just keep on adding new equipment all the time very quickly. We can also, now that we have all of this data sitting there nicely modeled, we can now flow it to other applications who are going to make good use of it. And we just introduced basically a publish-subscribe model. So the combination of these two systems allowed us to make the data generally available. So after that, so data is flowing out now. We're in a good kind of place. We can now take this information to additional services. In this case, we build a fault detector in IoT events. It's basically a simple rules engine that says, have you broken down 3 times? You haven't sent me a signal, therefore you must be faulty. So then we can take all this through some middleware. So this isn't really anything special. It's just glue with AWS, which is great for the stuff. And we just propagate the message along eventually to trigger an API to our maintenance system. And that's it, really. It was actually quite simple in the end once we got the right tooling in place. And this is what it looks like in real life. You can kind of see a blue tote. So this is where ingredients sit, ready for picking. It comes down the conveyor belt, and it's supposed to turn to the right. But it jumps in the corner, and a no-scan event is introduced. We notify the engineer via mobile app. They see the message, they accept it, and they're ready to go and fix the order. So the result was that MTTR started to collapse, and which is kind of the name of the game for day one. So what we learned is that once you start collapsing faults, you can also start seeing other things, because you can now go beyond reaction mode. We started noticing patterns. We have parts of the factory that, we call them rats, which basically take a box and move it from here to there, a right angle move. And all of them were failing in strange ways we couldn't piece together. But once we got the data out of the UNS, we could start seeing a pattern, and we discovered things we couldn't have before. So there was a mechanical fault in all of these things, and now we could fix that. We could start noticing wear and tear issues, and we could start altering our maintenance plans. So that was a big deal, make more efficient use of the engineers, and so on and so on. So the benefits start to pile up, unforeseen benefits as well. And we ended up with a new product architecture. Suddenly, we seem to have something on the go here. And we're ready to kind of keep going. So next, we thought, OK, we got data. Can we send it to the lake? Because once we do that, we can start doing all sorts of other good things. And this was quite easy. Because once we have the base architecture, the UNS, we can now just capitalize on existing infrastructure. So this stuff already existed. We plugged into a pipeline, and we can just move data to the lake. Once it's there, we can do analysis. We have whole teams doing analytics. We have reporting. We can do even model training, you'll see in a minute. So that's great. So next, we thought, OK, we're doing good here. What else can we do quickly? And we thought, let's try a hand at some predictive maintenance. Because much better than breaking down and chasing the box is not to break down in the first place. So the 30K I showed you earlier just doesn't happen. So again, the basic architecture is in place. So then we can add some sensors around our equipment. We can move, for example, temperature, variations in temperature, vibration. So if these go out of kilter, we can start thinking that maybe this machine is about to break down. And if that's true, then we can do something about it upfront before the breakdown happens. So we take this data, we give it to an anomaly service online, a SaaS solution, and then we stream it back into the UNS. But when it's in the UNS, we capitalize on the same middleware infrastructure that ultimately creates a works order. So the engineers don't even know the difference. They get a works order, and then just go and attend to the machine. That's what it looks like. So this is our factory. Our factory is kind of a three-dimensional cube. So imagine like a lasagna of three factories stacked on top of each other. So we have, what you're seeing there is a lift. So imagine a very kind of fast-moving lift up and down that's moving product. If one of those things, we got half a dozen of those, if one of those things break down, we have a very big problem. So we put a little sensor at the bottom. The sensor emits data. Alerts get picked up. And we do the works orders and goes round and round and round. So net result, significant downtime was avoided. Plenty of examples, so we started to win. Next, we thought, what else can we do? SCADA. We have a SCADA system. It came with the automation, but it was very basic. It had literally 10,000 lights that would flash. So if something goes wrong, it flash a red light, but it wouldn't tell you where it is, what it broken down. So somebody would have to physically go there, see it, and they just have to figure it out on the go. So we took the data out of HiByte and IoT Core and pushed it into Ignition, which is an industrial platform for building SCADA systems and other things. And literally within a couple of months, we had the whole factory had a SCADA system which was on click. It would show you all sorts of metadata we didn't have access to before. And we were able to put it up in a control room. Imagine a room full of screens, giant screens, so people watch them. They maintain situational awareness. They can just have complete visibility of everything that's happening and quite interactive. We also introduced IoT Sitewise, a great tool. We ingest data, so we can just do some analytics in the moment, usually for 30 days in our case. It can do more than that these days. And also some visualization, but it does a lot of other things too. So beyond SCADA, we thought, this is kind of a much bigger win. Where can we go next for that?
Where we went next was to add this OEE data I told you about before into this integrated system. And so with the availability of this data from the AWS IoT Core, we were able to make that calculation within Ignition and send that data live to our control room again. This is how the dashboard looks like. And this is some data that can be refreshed every minute or so, very rapidly. At the top right corner, you see a couple of bar charts over there, where the metrics I was telling you about before, the availability of your equipment, the performance, the quality, are available in real time. And so our operator in the control room are now able to see on a live basis how these metrics evolve against time, and possibly do something if something is breaking, adjust in real time. I've been telling you a lot about this OEE metric equation so far. Now, what we can also do with it is to express it at different level of granularity, all the way up from the enterprise down to a site, an area within your factory, a specific line, or even near stations. This metric can also be expressed in different slices of times. You can compute that across a shift for a full day of production, a week, a month, etc., etc. And what that allows you to do is to be able to identify the different areas of opportunity where your operation is not performing as well as you'd like. And so if you imagine a time for the next strategic investment, in which factory should we invest our dollars? Not sure. Let's look at our OEE data. And our recommendation is to prioritize those sites where you have the lowest OEE. For instance, imagine you've identified that there is a deficit of performance in the end of the line process, where boxes are put on pallets before they are shipped to our customers. Then you can have a number of options to invest into. Like you could automate the process, or you could resource it more, like add more capacity to that process. Possibly rebalance the type of labor you have there. All of this becomes possible because you have put the data in the system, and you had the way to measure it, track it, and evolve it. So that's about OEE. Next, let me tell you about our simulation capability. So this is something we are quite proud of. So let me run you through a little scenario. Imagine you're on the factory floor and you start seeing some box congestion along the line. Not quite sure what's happening. It's just a complex system, you know. So in this situation, everybody else does it the same way. You start to run some root cause analysis, detect what other metrics have gone wrong at the same time at that congestion. And maybe you've identified that you saw an increase in the number of box recirculation around the floor soon before the congestion happened. Okay, good. So now you have an hypothesis, like maybe if we were able to better treat the recirculation of boxes, we wouldn't see those congestion, or we could remove them faster. Now, the problem with all of this is you have no way of testing those hypotheses on the real floor because it's too costly and things break, and you are maybe at risk to missing the outload time, this box needing to go to your customers. And that's the reason why we built this digital system, digital simulation, where you're able to model these processes, these events, and test these models. So you could run a range of different parameters, like what if the level of recirculation is up to 10%? You run your model, you look at what happens, nothing happens. Okay, you're good. Run another scenario with 15% of recirculation in your floor. At that point, you start seeing some box clogging here and there, but it's okay. Turn the parameter up again, 20%, and everything suddenly gridlocks and nothing moves anymore. So having the ability to simulate these scenarios easily and quite fast, to be honest, now you are in a position to know what to do about your congestion. You've identified the root cause, and you can do something about it. So this is the real purpose of our digital capability. Now, let me take a few moments to tell you how we've built that capability. We've done something very simple, something very iterative. We use these three very simple steps. First, we modeled one of the important processes. Then we started playing with it, running experiments about that particular process. Fine-tune it a little bit, and once you're happy with how this process reproduces the reality you see on the floor, you move on to the next part of the model, the next important component. And so what we've done, we started small, model a station. How is it that the box, how long does it take for a box to be picked, for the ingredient to be placed in the box? Once we had modeled this particular process, we were able to measure on average, how long do boxes spend in station, the time they spend in station. Once we had that model, we chained a few of these stations together to create a leg. And once you have a leg, you're going to send a number of boxes to visit some station, this station, not that one, maybe you go to this one. And running a number of orders through that leg, now you are enabled to measure the number of station visits a box needs to make in order to pick all the ingredients that the customer have asked for. So that's the modeling the leg. Now, you want to extend the scope of that simulation a bit further. Once you have a leg, you're going to connect a few of them together so that you can model the process across the full floor. What's interesting about having access to a full floor is we have two different temperature zones in our factory. One zone where you pick only chilled ingredients that are going to be put in a separate section of the box on there. And after that, the box is going to move to the ambient side of the factory, where you're going to put the root vegetables and all the ingredients that do not require low temperature. So now that you've got the full floor, you're able to model and measure the time a box is going to spend on the line. And finally, as Thomas said earlier, our tower is made of a different number of layers, 3 in this site. So you connect the 3 floors together, and then you're able to measure the recirculation from one floor to the next that I mentioned earlier. And that's it. From 0 to 1, you've got a full factory model now. Now, along each of the steps I described before, we run a very important validation framework, and every time the same one. So every time we were iterating on that model, we always start by replaying past events. So you gather the data from past production and production days, what happened yesterday, the week before, and then you run that data through your simulation model and look at the output of this simulation. So on this diagram here, you can see the cumulative fulfillment of our boxes against time. One of the line is the real production data, the other is the replay that's gone through the simulation. And now you can measure the accuracy of that replay. And after a little bit of fine-tuning, obviously, you get to a point where you're happy with the accuracy of that simulation replay. And the reason that's important is once you have high fidelity for your digital simulation, you know that whatever predictions that's going to come out of this capability, you will have high confidence in those predictions. So once you've validated the tool, what you can do is run those scenarios I mentioned before. There are 3 types of scenarios that can be run through this simulation. The first one, most obvious one, there are a number of configurable in the factory I mentioned before. How many boxes can visit the leg at one time? How many loops can you do in the recirculation? Those are configurable. So you can run a number of tests in your simulated environment and figure out what's the best balance for these parameters. The next type of use case, we've got a number of data products that run along the line. I mentioned the routing system earlier, where the box stops, at what station box stops. These models are continuously improving and continuously being developed. You can test iteration release of these models in your simulated environment and see whether or not this is going to bring an improvement to your operation. And finally, the last type of use cases is what if you were to add another part in the factory, you had a conveyor belt here, or you remove some station there, what would happen? So you can run these things in a simulated environment. And that's how it looks like in the end. So on this little animation, you're seeing the full tower in not real time, but as a replay. So at the bottom, I don't know if you can see that well. At the bottom there, you see the box entering the tower. They're going to go up the ramp and queue up a little bit at the entry of the tower, where you have a queuing process that lets them drip feed the box one after the other. The boxes will enter different legs, as I was mentioning before. And going around the legs, those boxes can stop at the station where they need the ingredients to be put in the box. And so you visit one station, and then the box goes on the conveyor system again. It's going to visit another station, and another leg maybe, go pick the ambient food. And all that journey happens for every other box. Every box goes through the same journey with a different route. At the very end, you have these boxes here exiting the picking area and going towards the end of line where they will be put on those pallets I mentioned before so that they can be sent to our customer. And that's the power of the factory twin, the ability to replay any kind of event and test variation of these scenarios. So having access to this, we have a very nice success story that happened recently. I mentioned the importance of routing these boxes at the right station at the right time. Now, being able to access live data is extremely important to measure for instance, the availability of stock at specific station. Some stock is going to run down and you have to replenish it, but some stations sometimes are missing some stock. So knowing where the stock is and how much of it you have is very important for our routing process. And with access to real data, you can also anticipate the workload on those stations and make sure it's well balanced across the line. And so recently, we were able to use all of this data in a live fashion so that we can update the routes of the boxes where you anticipated the box to go. You can update that route for the best possible journey so that the box can pick the right ingredient at the right time. And this improvement had a significant impact on our operation efficiency. We've seen an uplift of more than 10% in our throughput recently. So this is a very big win for us. Last but not least, once you have all of these components connected to it, we have a number of warehousing system databases that we connect to, we query to access this stock data. Now, instead of querying the database directly, having everything connected through the UNS allows you to have access to that data as well in that unified space. And this is our solution from 0 to 1 that we've called Factory OS. Now, once we have this, here comes the big picture. What are we going to do next with it?
So we decided to kind of stop there. That's plenty to go from 0 to 1. And ultimately, this is where we want to go. So we had really enabled the accessing of raw data. We have built a UNS, and we started to reason, but weren't quite there yet. So we kind of looked back a little bit and said, if we keep on going, are there going to be any wheels that are going to come off? And the answer is, yep, there could be a few. First, we looked at our infrastructure. To begin with, everything was in a single server, and it doesn't require a genius to figure out that if that goes down, the whole factory now goes down because our factory totally depends on this. So we decided to introduce containerization. We introduced GitOps so that we can evolve patches and server releases. And effectively, we have a very resilient system, 100%. It never goes down. And by the way, we count availability in the OEE calculation. We include tech availability as well. So if we were to hit 98.5%, tech kind of has to be almost 100. We use Portainer, which is a local, on-premise containerization service. It's like Kubernetes on-prem. We could have used AWS, but all our infrastructure for latency reasons is on-premise. If you're using AWS Outpost, you have different options there. You could actually use an Elastic service or Kubernetes. The factory twin is going to get an upgrade.
So now that I've described how we've built our twin, what can we do with it after that? So I was telling you about this past event that you can replay You can access this data as live as can be in the factory room. You are able to test your assumption, find quicker resolution to incident. We want to connect this to the simulation capability so that on a very short time scale, you're able to test alternative scenario. Like you've detected that fault, you're going to have to introduce mitigation on a very short time scale, run a few scenarios, not a big grid, but just a few meaningful scenarios. This parameter, could we use this one or that one? And then find the better outcome from the simulation. At that point, you can reconfigure your factory with the right parameter for the right amount of time until you fix that fault. And you're able to keep on evolving this life. So from the digital twin I described, now you're entering a decision twin, where having access to these multiple sources of data live, you're able to test scenario instantly and potentially update this configurable I was telling you about. So all of this, you put it in the hands of the operator in the control room, and that allows to take the best decision at the best time. Next is Factory API.
So we had all these connections between systems. So remember, we want to command the factory. Once we figured out an optimization, we're ready now to tell the factory to do something so we can change its state for the better. But what we had was entanglement, which is the kiss of death in our platform. So we have systems like a SaaS solution talking to a JDA warehouse management system, and the two are aware of each other. You have a platform, Python program writing SQL, native SQL, and sending it down to the control. It's just a mess. And you can't run a system like this. So, the obvious answer, it doesn't, again, it's not rocket science. If one of these things starts going away, you will end up having to rewrite an interface. If you introduce two WMSs because you built another factory and you just want to go a different route, now you have to duplicate all of these and orchestrate which one you're integrating to. And it just goes on like that. So, the obvious answer is we need to introduce APIs. We need to abstract the factory from opinionated vendor implementations. We don't want to be aware that we have a JDA or a Manhattan. Nothing wrong with these systems, they're perfectly fine. We just don't want to be aware of them. We want to create a canonical version of what a warehouse system does, the way Gousto understands it, and we want to do this for everything. So when we say Factory API, we are talking really about lots of APIs. For maintenance, for warehouse management, for warehouse control, and so on and so on. So all of these together make the Factory API. So this is in progress, not yet achieved. And obviously the cherry on the cake is to kind of evolve from algorithmic decision-making to AI ML. So for example, this is something we're looking at now, this is the same reactive maintenance architecture. This is our first use case on, just a reminder, we take data from the factory, it goes into the UNS, make it useful, and then we do a simple if then else. If you haven't scanned for 3 times, as an example, you might be at fault, we'll raise a work order through that middleware. But what if we keep the middleware, because it creates orders, that's useful, but what if we take out the if then else type of logic and introduce something we can call the downtime predictor, for example. It's just a concept. So we take the data in for inference purposes and say, okay, I've seen this before, and when I see this, a few minutes later, something bad happens in the factory. And we can start this, applying it to all sorts of places in the factory and predict performance degradation. We could also, because you could have 20 of these on the go, which one do you attend to? Some of them are more severe than others. So you can start using AI to stack rank them and say, you have to go to these two, and these two have to wait. And we can hot swap that with an actual technical architecture we're looking at. So we can, again, just route machine data, put it through a Lambda that basically interfaces, orchestrates something like AWS SageMaker, and conducts the inference, and it produces a result and says, I predict that you might see downtime. We store that in a database, and if we decide that this is worthy of looking into, we raise through the middleware. We haven't altered that, that's still there. We raise a works order, an engineer goes there. Again, they don't know how, none of this is visible to them. They just attend to yet another works order. So we have a universal solution for everything. And a different architecture starts to emerge now. Closer to our vision, we get all the data, we make it useful through UNS, and we start reason on top of that data, and we start acting on it via APIs. And then if you take this one level up again, you start seeing a slightly different pattern emerging.
And what you can do when you have these predictors, these ML predictors, again, you can connect them to your factory twin and test alternative scenarios. If this downtime is going to happen at that given time, what is our best configurable to react to this as quickly as possible? That's one great use case. But of course, we've got more use case coming. What about this congestion detector I was talking about before? If we were to able to anticipate this congestion, what are the better configuration to prevent it or to mitigate it? How can we balance the line better? Sometimes bugs get stuck a bit in the chill zone, sometimes a bit in the ambient zone. If we are able to predict those imbalances, again, we can configure our factory live. All of these possible machine learning models to provide predictions, connect them to your twin, run a number of alternative scenarios, and find the best decision to answer these issues. Once you have that, you connect to your factory system through the factory API, and you get your factory reconfigured live like this. And with all of this complex orchestration in place, we reached the vision that we presented at the beginning. This now becomes reality. From the raw data from your equipment, you connect it to the UNS. That's going to generate the event from which you can learn. You run analytics and predictions. Those predictions will lead to command into the system, the decision we were talking about, that you can connect through the API, the factory API, that will send back the control to the equipment we mentioned before. And that's the factory tech at scale. Now, how could this be useful for you?
So, it's coming down to being able to move faster and go further. What this means is that you don't need any of this to solve problems. You could just use your engineering expertise and try to solve this. You will get up to a point, but you won't get there fast enough. And we thought that we did this analysis up front, and we found that we could get to something like 95% availability, but it'll take 12 months, maybe. Sometimes some problems were so tough, it could take years. So that costs a lot of money because downtime happens during that 12 months. And if you could do it in 6 months, it's worth it. You can also get further ahead because when you have data, you reach expertise will get you up to a point. There's a ceiling beyond which you just don't have data. You can't act. It's just you act on intuition. So that gets you much further ahead, and you can break that ceiling, go much higher. And also, when you solve problems like that, you usually focus on one area. You swarm around, or at least we do. We swarm in one area, then we move on to the next one. By the time you get to the next area, you have data. So that's very helpful. Other ways it can help is with integrations. Now, this is kind of what we had, and lots of manufacturers have. This is a typical pyramid, the automation pyramid, which is just a conception, but it usually, in our experience, results to a lot of point-to-point integrations and entanglement. And instead of seeing the world like this, what if you could see it more like this? So we have a hub in the middle, which adds value to the raw data, and we can start adding lots of spokes, which contribute with information, with data, and also can generate data and put it back into the system. An example is OEE, that Fabrice mentioned earlier. So we created a new spoke. We called it OEE, Manufacturing Execution System, OEE, that calculates quality, calculates performance, and so on. Now, you can take this data and put it up on display and have a dashboard and do something with it. But you could also put it back in again, and then other spokes that don't calculate OE but could benefit from it can do something useful with it. And so we develop network effects. Now, in terms of how to do it, think big, like we showed you, but start small. Start with a POC, get a small group of people, and start working on it. Deliver something. Find a good use case, build it up, make sure it's limited in time so it doesn't go forever. And once you achieve that, just add value, boom, boom, keep going, add value, keep going at breakneck speed, and eventually take a stop, scale the platform, and then you're ready to go to the moon. Now, you don't need a big team either. You just need one person to install the initial UNS system. And then as you encounter new use cases, then you find a data scientist, a data engineer. We literally added software engineers something like 7-8 months down the line, so you don't even need that to begin with. You don't need a big team, but when you're ready to scale, you do. And that's our team. Very proud of them. And at the bottom is the head of engineering who smiles a lot, so he's very happy. We definitely recommend to use standards. Don't go building things that you don't have to. Buy them. The great tools out there. I mentioned Hybrid, I mentioned AWS IT Core. Don't overthink the tooling. Just trial it. If it doesn't work, do a POC, move on. And don't do RFPs, write strategy papers. Just move quickly. That's our experience works the best. You don't need a big team. And a big software engineering team, that is. You have a lot of good tooling that takes you like 80-90% of the way. You definitely don't need to bring the factory down. If you pick up a quiet area to experiment, you can learn there, iterate, and then move on to more sort of critical areas. You don't have to, even if you don't understand the technology, the best thing to do is mesh teams together. Take people from mechanical engineering and software engineering or technology in general, put them together, and 1 + 1 = 3 will emerge. And that's the way they learn together from each other. You don't have to worry about having old equipment that doesn't communicate. Quite simply, attach detectors, like we showed you with predictive maintenance. They can measure all sorts of things with condition-based monitoring, and you can get going like that. And if your tech teams don't understand automation, make sure they go and live in the factory for a while. They literally need to go there and smell it. There's no other way. And even work there for a couple of days, they'll learn a ton and be very, very useful. It has to happen. And back to the beginning.
Indeed, this is where we started, except that now we know the state of everything as much as we can, and now we can reason about the data on top of it. So what problem can we solve? We've been solving for efficiency, as we described today, and keeping our operation efficient is what allows us to keep our food fresh before you receive it in those boxes at home, and keep our boxes affordable for our customer. And that is really the big win here. That's what matters to our customer. Thank you for listening to our story today. Before I let you go, feel free to reach out on LinkedIn. Our links are there. And please, I believe you're going to receive a notification about the session. If you could complete the survey, your feedback is very important to us. Thank you very much again.
Thank you.
Have you seen the clock?